Welcome back to part 4 of our ongoing discussion of how to graph polynomials. The last video ended pretty abruptly with me talking about multiplicity, and so we're going to get right back into that with this example. I have a new polynomial here. In the interest of talking about multiplicity in a really deep way without having to factor a 6th degree polynomial, I've created a pre-factored polynomial. So you'll have to trust me that if you actually multiply all these things out and like FOIL this one and then multiply by this one and like triple FOIL this piece here and then multiply it all together, this is a process that we could do if we had a spare half an hour and we're really bored. I don't have a spare half an hour. I'm not really bored. I'm going to skip doing that. But trust me that if we did all of that, you would end up with a very long, very elaborate polynomial that I don't want to have to try and factor. So instead, we're just going to look at this pre-factored thing right here, and we're going to start talking about the x-intercepts. X-intercepts happen when y equals 0. So that would give us 0 equals x minus 3 squared times x plus 5 cubed times x plus 2. So right away we can see that our intercepts should be x equals 3, x equals negative 5, and x equals negative 2. Here's the thing we have to pay very close attention to. This x equals negative 5 piece comes from this term, or I'm sorry, it comes from this factor, and there are 3 of those factors. So we say that this has multiplicity 3. The x equals 3 intercept comes from this factor, but there are 2 of them. So this has multiplicity 2. There's only one of these guys, so this has multiplicity 1. And multiplicity is going to affect what the graph does at that intercept. We're very used to the graph crossing the axis at an intercept, but that doesn't always happen. So when something has even multiplicity, gotta stop trying to write in black, it is not working. If something has even multiplicity, that means it bounces off the axis. Or I think the official math word that the book uses is that it turns. I like bounces. Bounces is just a much more fun word to say. If something has odd multiplicity, it crosses the axis. So at this intercept, this 3, 0 intercept, it's going to bounce because the multiplicity is even. At this one, it's going to cross at negative 5, 0. And at negative 2, 0, it's going to cross. If we're going to get extremely pedantic, at multiplicity 1, it sort of just crosses straight through. At multiplicity 3, it crosses. Multiplicity 3, it does cross, but it gets flat for a second first. So it kind of thinks about bouncing and then changes its mind and continues up. It goes flat for just an instant, and then it keeps going in the direction it was already heading in. Whereas something like this, it'll just turn around. So That's how the multiplicity affects what's going to happen with these intercepts. And it's something you have to be careful of so that you don't sort of fall into this trap that we ended up in with the last problem, where it looked like we should cross the axis, but our end behavior said to go down, but we ended up above. Those kinds of problems get solved when you're paying close attention to the multiplicity of your intercepts, so that you always know which side of the axis you're on. So I'm going to sketch a graph of this guy real quick. Or I'll try anyway. The y-intercept looks like it's going to be a mess. Y-intercept should be, when you plug in 0 for x, this piece will be 9 times 2 times 125. So 250 times 9 should give you 1,250? No. 2,250. Yeah. Okay. So the y-intercept is going to be obnoxious. We'll still do our best to graph it. We need to look at the end behavior as well. We can kind of see that the leading term is just going to be all these x's. So the leading term, I'll get 2 x's from this, 3 more from this for 5 x's. I'll end up with 6 x's in total if I were to multiply this whole thing out. The leading term would be x to the 6th. There would be other terms, but the thing in front would be x to the 6th. And that's all I need for the end behavior. X to the 6th looks like this, goes up, but all I care about is the ends. So, after all is said and done, I have there's 2,250 on the y-axis. On the x-axis, I'm going to need some of those. Okay. So, I have intercepts at 3, and this is a bounce. I have an intercept at -5, and this is a cross. And I have an intercept at -2, and this is a cross. And my end behavior is going to be up to the left and up to the right. Got that field goal end behavior. So from here I can come on down. I'll cross here. Or no, this is where it gets flat and then crosses. That's fine. I'll cross here. I'll pick up this 225. I'll bounce here, and I'm going in the correct direction after that bounce. So, this is how multiplicities work. They determine whether you cross or bounce. There's one more thing that I need to tell you about polynomials before I unleash you on the homework. And that is, we need to talk about the full spectrum of possible end behaviors. So at this point, I feel like we're pretty comfortable with the idea that end behavior comes exclusively from the leading term. And it turns out it's even simpler than just looking at the leading term. The end behavior is based entirely off of the exponent and the sign of the coefficient. So, you're going to look at the leading term. For end behavior. The first case we ever looked at was an even exponent and a positive coefficient. And that resulted in what I called the field goal. Up in both directions. Like a field goal. The second example we looked at had an odd exponent, but a positive coefficient. And that resulted in what we called disco right. Disco right. We've also looked at what happens when you have an odd exponent and a negative coefficient. That resulted in something that I called disco left, where it's going down to the left, down to the right, up to the left. And the only other combination that we can get out of this is using an even exponent and a negative coefficient. And in that case, it's going down in both directions, going down to the left and down to the right. And that is one that I affectionately call hammer time. That's it. That is the full list of end behaviors. Field goal, disco right, disco left, hammer time. Those are the only 4 options for polynomial end behaviors. In the last online meeting, the possibility of a T-pose end behavior was raised, and we're going to talk about that in the next section, 3.5, when we do rational functions. So look forward to that. It's a good time. For now, I'm going to call this finished. In this video, try these homeworks. Ask me questions about these homeworks when we meet in class for our conferences, and good luck.